Good morning, doctor. We are from group 15. We are going to present the Dolph-Chebyshev window, and the scenario we provide is low-pass filter. Our group member is Anas, Wong, and Yong. Okay, so what is this Dolph-Chebyshev window? From the diagram, from the figure above, we can observe that from the Dolph-Chebyshev window that it will produce that we have an equal height of the side loop, and also the main loop is higher than the side loop. And then this is the formula that we use in the Dolph-Chebyshev window. And the lambda is equal to amplitude of side loop divided with main loop amplitude. And beta is equal to cos h 1 over 2m cos h minus 1 and 1 over lambda. So what is Dolph-Chebyshev window used in? It is used in the signal processing. It processes all unequal side loop, just like just now I showed the figure right here. All the side loop has an equal height. So this window is used to process all unequal side loop level to be equal in magnitude, so they will have an equal amplitude. And then the method to obtain weight where side loop level can be specified to minimum possible non-bin weight. Chebyshev polynomial, first used by Dolph in 1946 to address the issue of designing radio antenna with the best directions properties. So from this, we can observe that Tn x is equals to cos n cos minus 1x, and the other one is cos h n cos h minus 1x. So there is the scenario we can use this. For example, when x is smaller or equals to 1, so we will use the above one. So when we derive it, for example, we put x is equals to 0, so t0 here will equals to cos 0 cos minus 1x. So cos 0 will equals to 1. That's why here t0x will equals to 1. For the second example is, for example, x equals to 1. So tnx equals to cos 1 cos minus 1. And then after that, we derive it, we will get t1x is equals to x. Okay, so for the x which is bigger than 1, for example 2, 3, 4, 5, so we will use the double angle trigonometric formula, this formula, and then after we derive, right, we will get this formula for the polynomial. Okay, so what is the objective for the Dolph-Chebyshev window? To achieve equal ripples of peak magnitude 1.0 in range of -1 and 1. So we use the Chebyshev polynomial and match them to audio frequency, which is called as AF. We only need the even order for Mach Chebyshev window, as only they are symmetric about time zero here. So stop band approximations error of filter design have essentially equal ripple behavior for the symmetric antenna area. So there has three conditions, right? So element at plus minus dn. So this is for example, this is negative dm, and then this is positive dm. The example given here is -1 and 1. So second element have the same weight bwn. So the weight is for this one. And then uniform spacing center is equals to 0. We can see that 0. Okay, next. So the filter order is estimated using this formula, n is equals to 2.056 lambda s minus 16.4 divided with 2.85 and then w. So where this w is the normalized transitions bandwidth. For a low pass filter, the formula is like that, ws is minus with wp. Okay, that's all from me.
Hi and good day, Doctor. I'm Yong from Group 15, Section 1. So first of all, I want to say thank you to Wong for a presentation just now. Okay, so I'm going to start my presentation with the concept of low-pass filter. First, I want to tell you about the function. Okay, so the low-pass filter allows only the passing of low-frequency signals by blocking or attenuating the high-frequency signals. So low-pass filters are usually used in these three fields: the acoustics, optics, and electronics. For instance, in acoustics, we have the audio amplifier, and we have also the equalizer. Okay. Next up, optics. We have the low pass frequency filter, and also low pass wavelength filter for light. Okay. And the last one, we have the electronics. Okay. So in electronics, we have the low pass RC filter. So the RC means resistor and capacitor. Okay. Alright. So in order to design or yeah, in order to design a low pass filter, first of all, we need to know about the order. So order, this one, n is ordered. And the right hand side, we have also the epsilon. So this one we need to calculate first, and we need to substitute into the formula of n, the order. Okay. And I want to mention about the parameters for in order to calculate the order. So we have these 4 parameters, which is very important. Okay, so first one, AP, is the passband attenuation, and next up we have AS, stop band attenuation, and the next one we have omega P, which is passband cutoff frequency, and last one, omega S, is stop band cutoff frequency. So these 4 parameters are very important in order to start to design our low pass filter. Okay, so once we already know this, the value of these parameters, and we can start to substitute into the equation. So AP, we need to substitute into the right hand side the formula of epsilon. Okay, and AP, the unit of AP is in decimal. Okay, and next up we have AS, substitute, and omega S or omega P. Once we already substitute all of this parameter, we will get a value of n. So what is the next step? Okay, so once we already know the value of n, we need to refer to the filter table. Let's say now the value of n is 3. Okay, now we go to the value table, filter table. Okay, so the order is 3, and we have the section 1 and section 2. What is this? I will mention later. And we also need to we also can refer to the f naught. Okay, so f naught is the frequency scaling factor, and we have also alpha. So alpha is nothing but 1 over q. So q is the quality factor. So you can try to use your calculator to calculate 1 over 1.7061. You will get this value. Okay. All right. So once we already know the order and all of these values, we can start to get the transfer function. Okay. All right. So let's say my topology, my circuit, I have 2 sections. Okay. I have 2 sections. I have two sections in my topology. So the first section in the topology, we will use the formula of second order low pass filter. Okay, so this one is the formula for the second order low pass filter. And the second section of our of our topology, we will use the first order low pass filter formula. Okay, all right. So let's start with the first section. Okay, we look at the table. The first section. Okay, so the first section 1.0688. So this one we will use in this formula, the second order low pass filter formula. So 1.0688. What is this? So this one is a value of omega n. Okay, omega n. Okay, so we substitute everything into the omega n, and k is 1. Okay, and q, what is q? So q is this one. Okay, 1.7061. So we can start to 1.7061 divided by 1.0688 divided by 1.061. We will get the value of 0.6265. So the transfer function of the second order will look like something like x squared 0.6 what else 0.6265 s plus the 0.6265 square. So you can try to calculate it. Okay, and next up we move to the second section. So the second section, we need to use the formula of first order low pass filter. Okay, so we can also, so the second section for the value of f naught, 0.6265. So that one is the value of omega naught. Okay, so we substitute. Okay, so we will get the value of the transfer function for the first order, which is 0.6265 over s plus 0.6265. Okay, so once we already get the transfer function, and next up we can start to build our topology. So this topology is just a simple example, doesn't relate to the value that I mentioned just now. Okay, so I just want to show you. Okay, so once we already build the topology, we can start to calculate the value of resistor, the value of resistance and the capacitance based on the formula, the transfer function that we get just now. So we can use this transfer function to calculate the value of resistance and capacitance for our topology. All right. And I forgot to mention one thing. So we can also use the transfer function to plot the graph. So this one we will show in the demo session later. Okay. Right. So last one, before I end my presentation, I'm going to mention some mathematical stuff in the low pass filter. Okay. So look at the formula at the right hand side. So voltage out equals to this one. Okay. Voltage in multiply xc over z. So what is xc? Xc is the capacitive reactance. Okay. So the formula of xc is equal to 1 over 2 pi fc. So f is a frequency. Like I mentioned just now, the low pass filter used to attenuate the high frequency signals. Okay, so look at this formula. So if the value of frequency increase, so the value of xc decrease. Okay, and we look at the formula of voltage out. Okay, so frequency up, xc down. So look at this formula, V in xc over z. So once the value of xc is decreased, okay, the voltage out will be decreased also. So that's how the some basic concept of the low pass filter. So if I increase the frequency, and the voltage out will be decreased. So based on the formula that I stated here. Okay. Okay, so before I end my presentation, I want to tell you about the conclusion, the overall steps in order to design the low pass filter. Okay, so first one we need to know about the order. Okay, first one we need to know about the order. The second step is we need to know about the value of the f naught, and q, etc. Okay, and the third step is we need to build the transfer function. Okay, and once we already know the transfer function, we can start to build our topology. And the last step is we can start to calculate the resistance and capacitance for our topology, and we also can plot the graph. And this one will be shown later in a demo session. Okay. So in MATLAB is pretty easy. We do not need to do all this calculation with some complex symbols or formula, because in MATLAB we have the function or the CHE1 or the Ched1 order. So that one is used to calculate the order, which is the first step. Okay, so we have the function in MATLAB which is a Ched1 order to help us to calculate the order. And next one we have the function to calculate the function in MATLAB to calculate the transfer function. So that one is named JB1, if I'm not mistaken, and which Anas will show you later. Okay. So, and we also have some function to help us to plot the graph in MATLAB. So, okay, so that's the end for my presentation. Now I will pass to Anas for the demo session. Thank you.
Hello everyone, I'm Anas and I'll do the demo session. So let's go directly into MATLAB to start the demo session. So I'll do first the Chebyshev window, then I'll do the Chebyshev low pass filter. I'll start by the Chebyshev window. In here we have an example where we created a 64-point Chebyshev window with a side loop attenuation of 100 dp. So I started by identifying two variables, L and R. L is equal to 64, which is the amount of points, and R is the side loop attenuation, which is equal to 100. And then I use this function to produce the Chebyshev window. It takes in L, the number of points, and R, the side loop attenuation, and it provides us with the Chebyshev window. Then I draw the window. So I'm going to run the code. Right here, as you can see, we have the main loop at around 25 and all the side loops at around negative 25. This is because we set the side loop attenuation to negative 100. So it goes from 25 to negative 25, which is a difference of 100. And we have here the leakage factor, which is equal to 0% because there is a high difference between both the main loop and the side loops. The leakage factor will decrease if we decreased the amount of attenuation. So if I made this 20, for example, and I run again, it will give me a higher leakage factor, as you can see in here. First of all, it goes from a little bit above 20 to a little bit above 0. So the difference is only 20. And because the difference is quite low, the leakage factor is a bit high, it's 23. The leakage factor will go even higher if I decreased the attenuation even more. So let's say 5, save and run. Alright, so as you can see here now, the leakage factor is way high, it's at 93, and you can hardly tell the difference between the main loop and the side loop. So as you can see, with as we decrease the attenuation, the side loop attenuation, the leakage factor increase. So this is all for the Chebyshev window, and let's go for the other one. Now let's go for the Chebyshev low-pass filter. So in here we have an example where we have data that's sampled at 1000 Hz, and we are going to design a low-pass filter with less than 3 dB of ripple in the passband defined from 0 to 40, and we are going to have at least 60 dB of ripple in the stop band defined from 150. So I started by identifying the variables that we have. So we got WP, this is the cutoff frequency, and the reason why I divided it by 500 is to get the normalized frequency. 500 is just the sample over 2, so this is just to get the normalized frequency. And we have the stop band frequency, which is 150, and again I divided by 500 for the same reason, to get the normalized frequency. Then we have the passband ripple, which is equal to 3, as you can see right here. And then we have the stop band attenuation, which is equal to 60. After identifying the variables, we use this function to get our N and WP. N is the lowest filter order, the one that we saw in the table previously in the video. And WP is the passband corner frequency. After getting N and WP, I passed it to this function to get the transfer function, this one, and then I plotted the frequency response. So let's run the code to check it. First, in here, as you can see, we can conclude that N is equal to 4 and WP is equal to 0.08. Now let's go to the graph. Alright, so we have the graph right here. At around here, which is 40, you can see it started going down. So this is the cutoff frequency. It started having an attenuation of 60, and it kept going down until around 150. This is where, around right here, this is the stop band frequency. After this point, all the signals are being filtered out or filtered away by the low pass filter, and it keeps going down until it reaches the end. So this is all for the Chebyshev low pass filter, and this is all for our presentation. I hope you enjoyed it.